In this video, we finished deriving the energies of the stationary states of a rigid rotor. The Schrödinger equation for the rigid rotor is h hat uppercase y of theta and phi equals E times uppercase y of theta and phi, with a Hamiltonian for the kinetic energy that I'm not going to write out again, and with the wave functions uppercase y that depend on the two angles theta and phi. We use it as separation ansatz. Y of theta and phi equals uppercase theta of theta times uppercase phi of phi to separate the Schrödinger equation into two equations. These two equations were one for phi and one for theta. The first equation, the one for phi, is fairly simple. 1 over uppercase phi d squared uppercase phi d phi squared equals minus m squared. This can be rewritten as d squared of uppercase phi d phi squared equals minus m squared times uppercase phi. The general mathematical solutions for these equations are uppercase phi of phi equals a times e to the plus I m phi plus b times e to the negative I m phi for completely arbitrary a and b and for any value of m. You can check this by substitution. Only a subset of these mathematical solutions are physical wave functions. In order to be physical, a function has to be single-valued. Now, phi describes the motion on a circle and wraps around after a full turn of 2 pi, so we need to require the function to be periodic to keep it single-valued. This means that uppercase phi of 0 has to be equal to uppercase phi of 2 pi. This in turn means that a plus b equals to a times e to the positive 2 pi I m plus b times e to the negative 2 pi I m. This in turn can only be the case if the exponential factors are both equal to 1, which in turn implies that m must be an integer. M equals 0, plus or minus 1, plus or minus 2, and so on. We have our first quantum number, m. The wave function for a given m is uppercase phi of phi equals 1 over square root of 2 pi times e to the positive I m phi, where the prefactor takes care of normalization. Let's move on to the second equation, the equation in theta. It is sine theta over uppercase theta d theta operating on sine theta times d uppercase theta d theta plus beta times sine squared of theta equals m squared, with beta equal to 2 ei over h bar squared. Working out the solutions of this is rather lengthy. We'll skip it here. At the end, we get many functions that satisfy this equation mathematically. However, not all of them are normalizable. In order to be physical, they must be normalizable. It turns out this is only possible under the following two conditions. First, beta must be equal to j times j plus 1, where j is an integer that's 0, 1, 2, or so on. This is our second quantum number. And the second condition, that the magnitude of m is smaller or maximally equal to j. Now we can combine this equation with the definition of beta from up here to get the expressions for the energies. We get Ej, with a subscript j to indicate that it depends on j, equals to h bar squared over 2I times j plus 1, with the quantum numbers j equals 0, 1, 2, and so on, and m equals 0, plus minus 1, and so on, all the way up to plus minus j. We have two quantum numbers, one for each degree of freedom. The prefactor in the energy expression is usually abbreviated as B. And is called the rotational constant. Most often it is given in wave numbers and denoted B tilde. The relationship is B tilde equals B divided by H times C. So these are the overall energies of the stationary states. We see that the energy depends only on J, but not on M. The states with different M but equal J are degenerate. For a given J, there are two J plus 1 degenerate states. So the degeneracy Gj equals 2J plus 1. What about the wave functions for the theta equation? The derivation of these functions is quite tedious. Let's take the results and combine them with the phi functions to give the full wave function uppercase Y. Those functions have the general form y jm of theta and phi equals s, which is a conventional sign factor, times uppercase n sub j and m, which is the overall normalization constant, times uppercase theta of j and magnitude m of theta, which is the function that depends only on theta from our separation ansatz, times e to the plus I m phi, which is the function that depends only on phi. All the superscripts and subscripts indicate on which quantum numbers the various terms depend on. These functions are called spherical harmonics. And are defined over the surface of the sphere, theta and phi. We will examine them more closely in a separate video. In summary, we solved the Shortening equation for the rigid rotor. The solutions depend on two quantum numbers, j and m. J runs from 0, 1, 2, and so on, and m runs from negative j to plus j. The energy is a function of j only, and there are two j plus 1 degenerate states for a given j. The corresponding wave functions are given here and are called spherical harmonics.